Have you ever stared at your car or maybe a beloved metal tool and just felt that familiar pang of frustration at the sight of rust? That creeping orange-brown menace that seems to appear out of nowhere. It's not just an annoyance, it's a multi-billion-dollar problem globally. Material deterioration is a constant, costly battle we're all fighting, often without even realizing it. Okay, let's unpack this. Today, we're embarking on a deep dive into the fascinating world of corrosion and degradation of materials. Our insights are drawn from the comprehensive chapter on this topic in Callister and Rethwish's Material Science and Engineering. Our mission for you, our curious learner, is to cut through the complexity and arm you with the essential knowledge of why materials fail and, maybe more importantly, how we can stop it. We'll explore metals, ceramics, and polymers, breaking down the mechanisms, the whys, and the crucial prevention strategies, all painted with words, no visuals needed.
And it truly is a universally important challenge. Think about it. From ancient structures slowly crumbling to the high-tech components in, say, a modern spacecraft, materials are constantly interacting with their environments.
Yeah.
And these interactions often compromise their usefulness and longevity. Our source material opens with a great visual.
Hmm.
The common beverage container is a perfect illustration of how different materials, aluminum for the can, glass for the bottle, plastic for another type of bottle, each face distinct challenges from their surroundings.
Right, different materials, different problems.
Exactly. For metals, we typically use the term corrosion. This describes the actual material loss, either through dissolving into a liquid or by forming a non-metallic film, like that rust you mentioned. Ceramics, on the other hand, are remarkably resistant to corrosion, usually only showing issues at extremely high temperatures or in very aggressive environments. They're already kind of stable. But for polymers, we shift to degradation. Here, the mechanisms are distinct. Polymers might dissolve, swell, or experience alterations at a molecular level due to things like radiation or heat. We'll explore each of these, starting with the heart of metal corrosion.
Okay, let's begin with corrosion of metals. This isn't just a simple chemical reaction, it's almost always an electrochemical process, meaning there's a crucial transfer of electrons happening. At its core are two fundamental reactions working together. First, there's oxidation, where metal atoms actually lose electrons, becoming positively charged ions. We call the spot where this happens the anode. Think of iron losing 2 electrons to become an ion, or maybe aluminum losing 3 electrons to become allo. That's the metal being eaten away, essentially.
Right. And then those freed up electrons have to go somewhere, and that's where reduction comes in. Here, another chemical species gains those electrons. This occurs at the cathode. You see various types of reduction reactions depending on the environment. For example, in an acidic solution, hydrogen ions, H, can pick up electrons to form hydrogen gas bubbles, HROs.
Ah, so you might actually see bubbling sometimes.
You could, yeah. Or if there's dissolved oxygen around, which is very common, it can combine with hydrogen ions or water to form either water or hydroxide ions. The point is, something has to consume those electrons freed by the oxidation.
Got it. Oxidation gives electrons, reduction takes them.
Precisely. And what's critical is that an overall electrochemical reaction is always the sum of at least one oxidation and one reduction.
Mm.
And the total rate of oxidation must precisely equal the total rate of reduction. There's no net charge accumulation. All electrons generated by oxidation must be consumed by reduction. It has to balance.
Makes sense.
Our source describes this with a diagram. Imagine a piece of zinc metal immersed in an acid solution. At some spots on the zinc surface, maybe tiny imperfections, zinc atoms are oxidizing, releasing electrons. Zn becomes ZnO plus 2 electrons. These electrons then travel through the electrically conductive zinc to other spots on the surface where hydrogen ions, H, from the acid, are waiting to grab them, forming hydrogen gas bubbles. That continuous flow from anode to cathode is the corrosion in action. It's like a tiny invisible battery actively eating away at your material.
A tiny battery. I like that analogy. So if these electrochemical reactions are happening, it leads us to electrode potentials. Not all metals give up electrons with the same ease, right? This tendency to corrode can be quantified.
Exactly. Some are more noble, less reactive. Others are more active, more willing to corrode.
Our source illustrates this with what's called a galvanic couple, like an iron-copper cell. Picture two separate systems, two half cells, one with iron in the solution of its ions, the other with copper in a solution of its ions. If they're electrically connected, perhaps through a wire, and the solutions are connected to, something interesting happens. Copper ions are actually reduced, meaning copper metal gets plated onto its electrode.
At the expense of the iron.
Right, at the expense of iron, which dissolves or corrodes. It becomes ions. And this setup generates a voltage, about 0.780 volts in standard conditions, indicating a driving force for that specific reaction.
A spontaneous reaction.
Yes, but now, get this. If we were to swap the copper for zinc, the roles completely reverse. Now, zinc becomes the one that corrodes, dissolving into ZO ions, and the iron is protected, acting as the cathode where reduction occurs. The voltage changes, too, to about 0.323 volts. These voltages are super important because they tell us a lot about the relative reactivity or nobility of different metals.
And to bring order to this, to compare apples to apples, we use a consistent way to rank these tendencies. It's known as the standard M series. To create this ranking, we basically compare the potential of all these different metal half cells to a universal reference point, the standard hydrogen electrode. Imagine an inert platinum electrode submerged in a specific acidic solution, 1 molar HO, with pure hydrogen gas bubbling over it at a set pressure and temperature. This setup is our arbitrarily chosen 0-volt reference point.
0 volts. Okay, the baseline.
Exactly. The standard M series then ranks metals based on their measured voltage relative to this hydrogen electrode. Under standard conditions, pure metal, 1 molar solution of its ions, 25 degrees C. Metals at the top, like gold and platinum, have positive standard potentials. They're considered noble and inert. They don't like to oxidize.
Oh.
As you move down the table, the potential becomes more negative. These metals are increasingly active, meaning they are more susceptible to oxidation and corrosion. Sodium and potassium are highly reactive, found at the very bottom with very negative potentials.
So lower down means more likely to corrode.
Precisely. The key takeaway. When you couple two different metals from this series, the one lower down the table will spontaneously oxidize and corrode, becoming the anode, while the one higher up becomes the cathode and is protected. This helps engineers predict which metal might sacrifice itself in a galvanic couple.
Okay, so this series gives us a prediction, but you said standard conditions. So what does this all mean for the real world, which is rarely standard?
That's a great point. The M series is an idealized ranking. Real-world conditions, like different ion concentrations or temperatures, do shift these potentials. There's actually an equation for this, the Nernst equation, which lets you calculate the potential under non-standard conditions. Our source even gives an example, I think it was nickel and cadmium, where simply changing the ion concentrations can actually reverse which metal corrodes. It shows just how much the environment dictates a material's behavior.
Wow, okay, so concentration can flip the script entirely.
It can. And for even more practical applications, especially in specific environments like seawater, engineers often turn to the galvanic series. This series offers a more realistic ranking, listing metals and, importantly, alloys based on their measured potentials specifically in seawater. It's incredibly useful because it reflects actual performance in a common corrosive environment. And you'll notice something interesting there. Some alloys might be listed twice, once in an active state and once in a passive state.
Ah, passive. That sounds important. We'll come back to that.
Definitely. It hints at how some materials can surprisingly protect themselves. But first, let's talk about rates.
Right. Knowing if it corrodes is one thing, but how fast is often the critical question for engineers.
Exactly. We quantify this with the corrosion penetration rate, or CPR. It's essentially the thickness loss of material per unit of time. How quickly is the metal thinning? It's typically expressed in practical units like mils per year, that's thousandths of an inch per year, hempi, or millimeters per year. There's a formula based on weight loss, density, area, and time. Generally, for many applications, a rate less than about, say, 20 mph might be considered acceptable, but it really depends on the component's lifespan and function.
Okay, so we can measure the rate, but what controls it? We know these reactions happen, but what stops them from just running away instantly?
Good question. Actual corroding systems aren't always at thermodynamic equilibrium. Those electrode potentials we discuss, the standard ones or even the Nernst-adjusted ones, represent the equilibrium state. In reality, when corrosion is actively happening, the actual potential at the anode and cathode surfaces shifts away from these equilibrium values. This displacement is what we call polarization.
Polarization, like a resistance.
In a way, yes. Think of it like that. The magnitude of this potential shift is known as overvoltage, often denoted by the Greek letter eta. It represents an extra energy barrier that has to be overcome for the reaction to proceed at a certain rate. This overvoltage is what actually limits how fast corrosion occurs. Without it, corrosion might be much, much faster.
Okay, so overvoltage slows things down. Are there different kinds?
Yes, there are two main types of polarization that control the rate of these electrochemical reactions. The first is activation polarization. This happens when the overall reaction rate is limited by the slowest step in a sequence of steps occurring right at the electrode surface. Remember our hydrogen evolution example. For an HU ion to become part of an HUO gas bubble, it has to migrate to the surface, maybe get absorbed, electrons have to transfer, two H atoms have to combine, then form a bubble and detach. The slowest of these steps acts as a kinetic bottleneck.
Like a toll booth on the reaction highway.
Exactly like a toll booth. It creates an activation energy barrier that requires some overvoltage to push the reaction faster. There's a relationship, often logarithmic, between this activation overvoltage and the rate of reaction, which we measure as current density.
Okay, that's activation. What's the other type?
The second type is concentration polarization. This occurs when the reaction rate is limited not by the steps on the surface itself, but by how fast the necessary chemical species, the reactants, like ions or dissolved oxygen, can diffuse through the solution to the electrode surface. At very low reaction rates, there's usually plenty of reactants right at the surface. But if the reaction tries to go very fast, or the reactant concentration in the bulk solution is low to begin with.
It uses them up faster than they can arrive.
Precisely. You create a depletion zone near the electrode where the reactant concentration is much lower than in the bulk solution. At this point, the reaction rate becomes limited purely by how fast diffusion can resupply those reactants. It's like a supply chain issue for the reaction. The rate hits a limit based on diffusion speed.
So activation is about the surface reaction steps, concentration is about reactant supply.
Correct. And often, the total polarization is a combination of both.
So how does understanding polarization help us predict actual corrosion rates?
Great question. By plotting the polarization curves, how potential changes with the logarithm of current density for both the oxidation reaction, the metal dissolving, and the reduction reaction, like Hay reduction, on the same graph. Well, these curves will intersect. The point where they intersect gives us two crucial pieces of information: the actual potential the corroding metal will sit at, called the corrosion potential, VC, and more importantly, the rate at which both reactions are occurring, called the corrosion current density, IC.
Ah, and that current density tells us the rate.
Exactly. That corrosion current density, IC, can be directly plugged into an equation, like equation 17.24 in the text, to calculate the actual real-world corrosion rate, often expressed back into CPR units like mils per year. So these polarization measurements and plots are how engineers take the theory of electrochemistry and apply it to predict, quantitatively, how quickly a component might degrade in a specific environment.
That's really powerful, taking it from theory to actual prediction.
It is. And building on that, we encounter that fascinating phenomenon we hinted at earlier, passivity. What's truly intriguing here is that under specific environmental conditions, some metals that are normally quite active based on the M-series metals like chromium, iron, nickel, titanium can actually lose their reactivity and become incredibly inert, almost noble.
How do they manage that?
They form a very, very thin yet highly adherent and continuous oxide film on their surface. This film isn't like thick rust. It's often only a few nanometer thick, but it acts as a highly effective protective barrier, essentially stopping further interaction between the metal and the environment.
So it's like the metal puts on a protective raincoat.
A very thin, very effective raincoat.
Right.
Stainless steels are the classic example. They contain at least 11% chromium. It's the chromium that allows them to form this passive chromium oxide film in oxidizing atmospheres, making them highly corrosion resistant. Aluminum also passivates very readily in air. However, and this is critical, this protective film isn't invincible. A change in the environment, maybe the presence of certain ions like chlorides, or a change in acidity, can damage or break down this passive film locally. If that happens, the corrosion rate can suddenly jump dramatically, sometimes by orders of magnitude, maybe 100,000 times faster. So passivity is powerful, but it can be precarious.
You can actually see this behavior on those polarization curves we discussed.
You can. For a passivating metal, the polarization curve for oxidation has a characteristic S-shape. At low potentials, the current density increases, as expected. That's the active region. Then, as you increase the potential, the current density suddenly drops to a very low value and stays low over a range of potentials. That's the passive region, where the protective film is stable. Finally, at even higher potentials, the current might shoot up again. That's the transpassive region, where the film might break down or a different reaction starts. Where the reduction reaction curve intersects, this S-curve determines the corrosion rate. If it intersects in the passive region, the rate is incredibly low. If conditions change and it intersects in the active region, the rate is much, much higher.
That S-curve really tells a story about the material's response. Okay, but besides the material itself and passivity, what other factors play a big role?
Well, various environmental effects are huge. We mentioned concentration already. Fluid velocity is another. Higher velocity often increases corrosion, partly due to erosion wearing away protective films. Temperature almost always increases corrosion rates, as most chemical reactions speed up when hotter, and even things like cold working a metal, deforming it to make it stronger, can make it more susceptible. The areas with higher internal stress, like the head of a nail or a bend in a pipe, often corrode preferentially.
Right, so the environment and even the history of the part matter. And you mentioned corrosion isn't just one thing, it shows up in different ways.
Exactly. It's not always just uniform thinning. Our source identifies several distinct forms of corrosion, each with its own look and mechanism. Understanding these is key to diagnosing and preventing failures.
Okay, let's run through them. What's the most common?
Probably uniform attack. This is the general rusting or tarnishing you see distributed more or less evenly over the entire exposed surface, like that old car sitting outside. It's actually the least damaging in some ways because it's predictable. You can measure the rate and design for it, maybe by making the part thicker initially.
Predictable is good. What's next?
Galvanic corrosion. We talked about this one. It happens when two dissimilar metals are electrically connected while immersed in a conductive liquid, an electrolyte. The less noble metal, the anode, corrodes preferentially, while the more noble metal, the cathode, is protected. Think steel screws into brass. Fitting in seawater, the steel will corrode rapidly. A key factor here is the area ratio. If you have a small anode, like those steel screws, connected to a large cathode, like the brass plate, the corrosion on the small anode will be very intense because all the cathodic reaction is driving corrosion on a tiny area.
So, rule of thumb, avoid small anodes connected to big cathodes if you can.
Definitely. Or electrically inflate them. Or choose metals closer in the galvanic series.
Okay, what about corrosion that hides?
Yes. That brings us to localized corrosion, which includes crevice corrosion and pitting. These are particularly insidious because they can cause failure with very little overall metal loss. Crevice corrosion happens in tight, shielded spaces under washers, gaskets, bolt heads, even under deposits of dirt or scale. Inside the crevice, the oxygen gets used up quickly, so the metal inside the crevice starts oxidizing, acting as the anode, while the area outside, with plenty of oxygen, acts as the cathode. This creates a concentration cell, often leading to a buildup of positive metal ions and negative chloride ions inside the crevice, making it highly acidic and aggressively corrosive.
So the tight space itself creates the problem.
Yes, by restricting oxygen access and allowing chemistry changes. Pitting is similar, but occurs on open surfaces. It forms small pits or holes that can penetrate deeply and quickly into the metal. It's often initiated by a local breakdown of a passive film, perhaps at an inclusion or scratch. Like crevice corrosion, it's very dangerous because it can perforate a tank or pipe wall while the rest of the surface looks fine.
Nasty. Okay, what else?
There's intergranular corrosion. This is selective attack right along the grain boundaries of the metal. The grains themselves might be fine, but the boundaries corrode. This is a major issue in some stainless steels if they've been heated improperly, say during welding. This heating can cause chromium carbide particles to precipitate along the grain boundaries. This depletes the chromium right next to the boundary, making those narrow zones susceptible to corrosion, almost like tiny galvanic cells are set up. It's often called weld decay.
Weld decay. Yeah.
Then you have selective leaching, where one element is preferentially removed from a solid solution alloy. The classic example is the dezinsification of brass, where zinc is selectively corroded out, leaving behind a weak, porous structure of copper. The part might look okay externally, but have no strength left.
Wow. And corrosion interacting with physical forces.
Yes, two important ones there. Erosion corrosion is the combined action of chemical attack and mechanical wear from a moving fluid. Think of slurry pipelines, kite elbows, propellers, pumps. The fluid flow, especially if it contains particles or bubbles, can continually remove protective films or the metal itself, accelerating corrosion. You often see grooves, gullies, or wavy patterns. And then there's stress corrosion cracking, or SCC. This is a really dangerous one. It requires a simultaneous presence of tensile stress, either applied or residual, and a specific corrosive environment. It results in brittle fracture of normally ductile materials, often along specific paths like grain boundaries. The cracks grow perpendicular to the tensile stress, and failure can occur at stress levels far below the material's normal yield strength. It's a major concern in things like bridges, aircraft, and power plants.
That sounds incredibly difficult to predict.
It can be. Even residual stresses left over from manufacturing can be enough to cause SEC if the environment is right.
And one more type you mentioned.
Hydrogen embrittlement. Now, this isn't strictly a form of corrosion itself, but more a mechanism of failure that's often caused by corrosion reactions or certain processing steps. Atomic hydrogen, which can be produced during corrosion, like that cathodic reduction or pickling or plating, can diffuse into the metal lattice. Once inside, it can significantly reduce the metal's ductility and fracture toughness, leading to brittle failure, sometimes delayed, underapplied, or residual stress. High-strength steels are particularly susceptible.
Okay, that's a lot of ways things can go wrong.
It highlights how complex material-environment interactions can be, and the environments themselves vary widely. The atmosphere, with humidity, pollutants, aqueous solutions like fresh water, and especially corrosive seawater, soils, acid, bases, organic solvents, molten salts, and high-temp processes, even the human body for medical implants. Each presents unique challenges.
So, given all these failure modes, how do we fight back? What are the main corrosion prevention strategies?
Broadly, there are several approaches. The most obvious is careful material selection, choosing a material that's inherently resistant to the specific environment it will face, using stainless steel instead of plain carbon steel, for example. Another is environmental alteration. Can you make the environment less corrosive? Maybe lower the temperature, reduce fluid velocity, remove dissolved oxygen, or change the concentration of corrosive species. Sometimes you add inhibitors, chemicals added in small amounts that slow corrosion, maybe by forming a protective film or interfering with the electrochemical reactions. Good design is also crucial, avoiding crevices, ensuring drainage, preventing stagnant areas where corrosive species can concentrate, and, of course, applying coatings, painting, plating, enameling to put a physical barrier between the metal and the environment.
Coatings make sense. What about that cathodic protection you mentioned earlier?
Ah, yes, cathodic protection. This is one of the most effective methods, particularly for large structures like pipelines, ship hulls, or storage tanks. The core idea is to make the entire structure you want to protect into the cathode of an electrochemical cell. If it's the cathode, only reduction can happen there, meaning the metal itself cannot oxidize, it cannot corrode.
So, you force it to be the place where electrons are accepted, not given up. How do you do that?
Two main ways. The first uses a sacrificial anode. You electrically connect the structure, say a steel pipeline, to a block of a more active metal, something lower in the galvanic series, like magnesium, aluminum, or zinc. Because the magnesium or zinc is more active, it becomes the anode and corrodes preferentially, sacrificing itself while supplying electrons to the steel, keeping the steel cathodic and protected.
Like in galvanized steel.
Exactly. Galvanizing steel involves coating it with zinc. The zinc acts as a barrier coating. But even if the coating is scratched, exposing the steel, the surrounding zinc will act as a sacrificial anode, protecting the steel at the scratch. It's dual protection. You see, sacrificial anodes bolted onto ship hulls or buried alongside pipelines, they just need periodic replacement as they get consumed.
Okay, that's clever. What's the second way?
The second method is using an impressed current. Here, you use an external DC power source, like a rectifier. The negative terminal of the power source is connected to the structure you want to protect, making it the cathode. The positive terminal is connected to an inert anode material, like graphite or special alloys, often buried nearby. The power source then forces electrons onto the protected structure, preventing it from corroding. This requires a power supply, but allows for protection of very large structures and finer control.
Impressed current. Got it. So we've covered liquid corrosion pretty thoroughly. But what about just air? Does metal just sitting in dry air corrode?
Well, not corrosion in the sense of wet electrochemical cells, but we do get oxidation in gaseous atmospheres, especially at higher temperatures. This is often called scaling or tarnishing. Here, the metal reacts directly with gases, typically oxygen in the air, to form an oxide layer or scale on the surface.
Yeah.
It's still fundamentally electrochemical, though. You can think of metal ions forming at the metal scale interface, oxygen ions forming at the scale gas interface, and these ions and electrons have to move through the growing oxide scale for the reaction to continue.
So the scale itself plays a role in how fast it happens.
Absolutely crucial role. And whether that scale is protective or not depends heavily on its properties, which can be roughly predicted by the Pilling-Bedworth ratio, or PB ratio. This is simply the ratio of the volume of the oxide formed to the volume of the metal that was consumed to form it. If the PB ratio is less than 1, the oxide volume is too small to cover the metal surface completely, so it's porous and unprotective. Oxidation continues easily. If the Pb ratio is much greater than 1, say greater than 2 or 3, the oxide layer is bulky and tends to develop high compressive stresses as it grows, causing it to crack and flake off, spall, constantly exposing fresh metal underneath. Also not protective. The ideal case is a Pb ratio close to 1. This tends to form a dense, adherent oxide layer that can be protective, slowing down further oxidation. Metals like aluminum, chromium, and nickel often form protective oxides.
So that ratio is a key indicator for high temperature oxidation resistance.
It is. And the rate at which this oxide grows over time, the kinetics, also depends on the nature of the scale. It can follow different mathematical laws. Parabolic growth if diffusion through a dense scale is controlling. Linear growth if the scale is porous or keeps flaking off, or even logarithmic growth for very thin films at lower temperatures.
Okay. Now, briefly, what about nonmetals? How do ceramics handle corrosion?
Ceramic materials are generally much more resistant to corrosion than metals, especially at room temperature. Think about it. Many ceramics are already oxides or other stable compounds. They're already corroded in a sense. Their degradation usually involves simple chemical dissolution in certain acids or bases, or attack at very high temperatures, rather than the electrochemical processes we see in metals. Their inertness is why they're used in such harsh, high-temperature environments.
Makes sense. And finally, polymers. You called it degradation.
Right. Degradation of polymers. They don't corrode electrochemically, but they do deteriorate through various physiochemical processes when exposed to certain environments or energy sources. One major form is swelling and dissolution. Polymers can absorb liquids, especially solvents that are chemically similar to them. This absorption causes the polymer chains to separate, leading to swelling. The material gets softer, weaker, more ductile, and its dimensions change. If the polymer and solvent are highly compatible, this can continue until the polymer completely dissolves. Think about certain plastics dissolving in acetone, for example.
Right, I've seen that happen.
Resistance to this depends on factors like the polymer's molecular weight. Higher is better. Whether it's cross-linked prevent chains from separating, and its degree of crystallinity. Crystalline regions are harder for solvents to penetrate. Lower temperatures also slow it down.
Okay, smalling and dissolving. What else happens to polymers?
Another critical degradation mechanism is bond rupture, also called scission. This is the actual breaking of the covalent bonds within the main polymer chains. When chains are broken, the average molecular weight decreases, which usually leads to a reduction in strength and ductility. The material might become brittle.
What causes these bonds to break?
Several things. Radiation is a big one, high-energy radiation like gamma rays or electron beams, but also, very commonly, ultraviolet UV radiation from sunlight. UV light has enough energy to break many types of chemical bonds found in polymers. This is why many plastics become brittle, discolored, or chalky after prolonged sun exposure. Think faded car dashboards or brittle lawn furniture.
UV damage. Very familiar.
Then there are chemical reaction effects. Certain chemicals, notably oxygen and ozone, can react with polymer chains and cause scission. Ozone is particularly damaging to rubbers that contain double bonds in their chains, leading to cracking, especially if the rubber is under stress, like cracks in the sidewalls of old tires. And thermal effects. Simply heating a polymer could provide enough energy to break bonds. The temperature at which this becomes significant depends on the bond strengths within the polymer. That's why Teflon, a fluorocarbon with strong CF bonds, is much more heat-resistant than, say, PZC with weaker CCl bonds. All these factors, UV, oxygen, temperature, water absorption, often work together in what we call weathering, the degradation of polymers due to outdoor exposure.
Wow, okay. So polymers have their own unique set of vulnerabilities. What a deep dive today. This has covered a huge amount of ground.
It really has. It's a complex but vital area of material science.
So, to quickly recap for everyone listening, we saw that metals typically corrode via electrochemical processes involving oxidation and reduction, and the rates are governed by factors like polarization. We explored the fascinating phenomenon of passivity, where some active metals can form thin, protective oxide films, giving them excellent corrosion resistance. We learned that corrosion isn't monolithic. It manifests in many distinct forms: uniform, galvanic, crevice, pitting, intergranular selective leaching, erosion corrosion, and stress corrosion, cracking each with unique characteristics and prevention strategies. And we touched on hydrogen embrittlement as a related failure mode.
And we saw that prevention is multifaceted, involving careful material selection, altering the environment using inhibitors, smart design, applying coatings, and employing powerful techniques like cathodic protection.
Then we shifted gears, noting that oxidation in gases is also crucial. governed by the properties of the oxide scale, summarized by the Pilling-Bedworth ratio. And finally, we contrasted this with ceramics, which are generally very inert, and polymers, which degrade through physiochemical routes like swelling, dissolution, and bond rupture caused by radiation, chemicals, or heat.
And understanding all these degradation processes isn't just academic. It's absolutely essential for practically everything we design to build. From durable infrastructure like bridges and pipelines to reliable medical implants that have to survive inside the human body to just ensuring our everyday consumer products last as long as they should. The battle against material deterioration is definitely an ongoing one, but armed with this kind of knowledge, engineers, designers, and even informed consumers are better equipped to be part of the solution, choosing and using materials wisely.
Absolutely. And think about the challenges engineers face right now designing materials for the next generation of reusable spacecraft that face extreme reentry conditions, or materials for sustainable energy technologies like wind turbines or hydrogen fuel cells, which often operate in incredibly harsh corrosive environments. It isn't just about stopping rust on a garden gate. It's about pushing the boundaries of what materials can endure, enabling future technologies. And that understanding really starts with the fundamentals we've discussed today. We really hope this deep dive has given you a shortcut to being well informed on corrosion and degradation, and maybe sparked your curiosity to learn even more. Thank you so much for joining us on the deep dive. And on behalf of the entire Last Minute Lecture team, thank you for tuning in.